Okay, we're going to talk about the last section of Chapter 11 that we're doing, hypothesis testing with two population proportions. Let me get my laser pointer here. Come on, there we go. There we go. We've got the correct objectives this time. Form a hypothesis test with comparing two population proportions. And we have some criteria that have to be met in order to do this. We have to have a random sample. The samples need to be independent. Both samples need to meet a binomial distribution, so it's got to, needs to be a pass-fail type thing. Agree, disagree, only two possibilities. And as with other things we saw with hypothesis testing with proportions, the sample size times the proportion has to be greater than 5, in this case for both proportions, and the sample size times 1 minus the proportion has to be greater than 5, again for both populations. When that's true, we can apply the central limit theorem, and as we saw with other hypothesis testing, we'll be using a z-score and a standard normal distribution. And again, as we saw with the first couple sections in Chapter 11, we're going to rewrite the hypothesis as in terms of the difference between the two proportions. And it's going to be more useful in terms of calculating our test statistic, just like it was with section 11.1 and 11.2, where we're using the difference between the two means as what we're defining the hypothesis on, because that comes into the test statistic calculation. We are adding the weighted estimate of the common population proportion, which we'll call P bar. Okay. This is just a repeat of those conditions. Again, binomial distribution for the samples. These sample size limitations, independent samples, random samples. In this case, with those conditions met, here's our test statistic. We've got the difference in the sample population proportions minus the difference between the presumed population proportions that we would use in our hypotheses. And we've got sample size down here, and we've got this weighted estimate of the common population, which we'll define in just a moment. It shows up right down here. Okay, so that weighted estimate of the common population proportion is the sum of successes in both samples. So if I'm divided by the sample sizes. So if I'm given something like 5 in 10 dentists prefer 5 in 10 dentists in Minnesota prefer Trident, and 6 in 10 dentists in Wisconsin prefer Trident, then I'd have 5 plus 6 over 10 plus 10. 11 and 20 dentists overall is the weighted estimate of common population proportion. All right, so for example, if the mayor's chief of staff thinks that a local newspaper article has changed the way the community thinks about the mayor, he pulls the approval ratings before the article came out and compares it to the approval ratings after the article, which sounds a lot like section 11.2, where we've got, where we've got before and after, but we don't necessarily know that these are pairs. We've got some random sampling before and some random sampling after, so they're not paired. I can't track how it changed individuals' thoughts. So really I've got two independent samples here. They're not they're not dependent on each other. So 480 out of 1200 thought the mayor was trustworthy before the article. 550 out of 1180 thought he was trustworthy afterwards. So we want a 5% level of significance to test the claim that the mayor's approval rating has increased. All right, so let's start with what is our null and alternative hypothesis. So again, we're going to have population 1 be the opinion before the article, and population 2 be the opinion after the article. So the claim is that the proportion of voters before was lower than the proportion of voters after, so P1 is less than P2. We move that P2 over to, so we've got the proportions all on the same side. P1 minus P2 is less than 0. So that's our research hypothesis. We can write it, there we go, alternative or research hypothesis, P1 minus P2 is less than 0, meaning that P2 is going to be greater than P1. The logical opposite is that P1 minus P2 is greater than or equal to 0. All right, so which distribution do we want to use, and what test statistic is appropriate, and what is our level of significance? We're looking at the difference between two population proportions with large independent samples, so we're going to use a z-test statistic. The level of significance was given as 0.05. So what do we have here for our necessary statistics? We have sample proportion 1 is 480 over 1200 of 0.4. Sample proportion 2, 550 over 1180 is about 0.466. We're going to need our weighted, I've already forgotten the exact term for it. We're going to need p-bar, that weighted summed proportion estimate. So we've got x1 of x2, that's going to be 480 plus 550, and sample sizes for each, 1200 and 1180. That's approximately 0.4327. Okay, so we can put all these into our formula. There's P1, which was 0.4, P2, which is 0.466 something. Null hypothesis is that is 0, right? The 0.433 0.4327 that we just calculated goes in there, and then that's 1200 and 1180, our sample sizes, like so. So we get about 3.25. Right, P1 minus P2 equals 0 because that's the null hypothesis assertion, that it's greater than or equal to 0. Okay, so now we need to draw a conclusion and interpret this. So this is a left-tailed test because we're looking for the p-value. We want the probability that something is less than something else, which correlates to looking out for something on the left-hand side of the standard normal distribution. So we've got 3.25 is our calculated test statistic. We can look up the p-value associated with that, which they are not going to give us on this slide. So p-value from the tables is 0.0006. That is less than our 0.05, so we can reject the null hypothesis, and there is sufficient evidence at the 5% significance level to support the claim that the approval rating has gone up. Okay. All right. So we've got students at a driving school. Actually, we've got two driving schools, Pass with Pops and Flint School of Safe Driving. These are their pass-fail results, so this is a binomial distribution. It's either pass or fail, two options, by for 2. We've got that data. We want to use a 10% level of significance to test whether the passing proportions are different. So let me go back here. You may want to, let's see, this sample size is going to be 17 plus 8 is, 25 total. So 17 of 25 pass, 8 of 25 fail. This is 29, 23 of 29 pass, 6 of 29 fail. Okay, go ahead and get calculated, and we'll, unpause when you're ready to move on, and we'll look at what's happened here. All right, let's start with the null and alternative hypotheses. We'll set population 1 as flints, population 2 as pops. The claim is that the passing proportion in flints is different from the passing proportion in pops, so this is going to be two-tailed, right? We're claiming that the two proportions are not equal, which you can, claim proportion 1 is not equal to proportion 2. You can bring the proportions all to the same side and claim that the difference between the proportions is not equal to 0. So to put these in the form we're used to seeing, we've got the null hypothesis that the difference between the proportions is 0, and the research hypothesis that the difference between the proportions is not 0. I do like using research hypothesis instead of alternative hypothesis because it honestly makes more sense to me, thinking about it as, this is what I'm researching. I can make sense of the alternative hypothesis as this is the alternative to the null hypothesis, but it means the same thing, just whatever helps you remember it. Okay, so what distribution do we want to use, and what test statistic is appropriate, and what's the level of significance? So again, we're looking at the difference between two population proportions. They're fairly large samples, so we should use the z-test. These are small enough at only 25 and 29 that I would probably want to double check the numbers, although thinking about it, you've got the test you do with sample size times proportion should get you to these values here. So 25 times whatever 8 over 25 comes to should get me 8. So I can just read these values off and note that nothing's less than 5 and say, okay, I meet that criteria. In this case where I've got the x values directly. Okay, we did that. We're given a 10% level of significance, or alpha equal 0.1. So we need to calculate our statistics. They're doing this on the TI-8384. So we do need a couple of things from each sample to use the calculator. We need the x, the number in the sample with the characteristic we're evaluating, and the sample size. So we're calculating passes. So we've got 17 for flints, and out of 17 plus 8 is 25. I did that right in my head, yay me. 23 passes for pops, out of 23 plus 6 is 29, so we've got those. I can tell the calculator I want to do a 2-prop z-test. I can give it the x and in values appropriate, 17, 25, 23, and 29. Tell it I'm doing a two-tailed test by saying that my alternative hypothesis is written in the not equal to form. And select enter, and it will spit out these results. There's my z value. There's my p value is 0.34. So the next step is to draw a conclusion and interpret the decision. I've got that p-value of 0.344. I am looking for a p-value of less than alpha. Alpha was 0.1. My p-value is greater than 0.1, so I fail to reject the null hypothesis. There's not enough evidence to support the claim that the two schools have different passing proportions. Hopefully that was all fairly clear. Please feel free to get in touch with me with any questions you may have, and have a good weekend.